Now we're going to look at exponential functions. An exponential function is of this form that's given here. And before I talk about that, let's just give an example. F of x equals, let's say we've got some number 5 times another number, let's say 4, that has an exponent of x on it. That would be an example of an exponential function. All right, so now let's look at the definition. So the definition says exponential function has this form: f of x equals uppercase C times a to the x. So in this case, our uppercase C is like the 5 and the a is like the 4. So our only constraints on A and C are that A is greater than 0, not equal to 1, and that uppercase C does not equal 0. For all exponential functions, the domain is all real numbers, and the range is going to depend on what C and A are. This number A that has the exponent of x is the base of the exponential function. Now let's look at differences with polynomial functions. So polynomial functions, the variable x, it is the base, right? And it has an exponent that is a number, and specifically it's an integer, but it is a number, some fixed number. All right, so if we now look at exponential functions, right, here's an example. F of x equals 8 times 2 to the x. The variable is the exponent, and the base is a number. All right, so we're switching around which is the variable. All right, what we've looked at so far, we've always had x being the base. The variable has always been the base, and then we have some fixed number as the exponent. Now we're switching it around where the exponent is the variable and the base is a number. Now we're going to evaluate some exponential functions. Just like any other function, if whatever value we plug in here, this is x. So whatever number we have in there, we're going to plug in for x. So we're going to take f of 3, so that's going to be 2 times 4 to the 3. We replace that x with a 3. Now, remembering our properties of exponents and order of operations, that 2 stays out in front, and we're first going to apply the exponent of 3 to the 4. It only applies to the 4 because the 2 is just out in front. We do the exponent first. 4 to the third is 64. And now we multiply by 2 and we get 128. All right, now let's take f of negative 2. So x is equal to negative 2. So we're going to have 2 times 4 to the exponent of negative 2. So now we apply that negative 2 as an exponent to 4. So remember, a negative exponent means that we are taking the reciprocal of the 4, and then we have a positive exponent of 2. So we get 2 times 4 squared, or 16. Simplifying that, we end up with 1/8. Okay, 4 to the 0. So again, this means that x is equal to 0. So we got 2 times 4 to the 0. So 2 times 4 to the 0. So anything that has an exponent of 0 is going to result in 1. So we get 2 times 1, so we get 2. Here we have another example. So first we're going to plug in a 3. So we've got 2 times negative 3 to the 3. Now, we got to be careful with our order of operations here. The negative 3 is not in parentheses, so that exponent of 3 only applies to the 3. So that negative is still there. We take 3 times, or 3 to the third, which is 27. So we end up with a negative 27. So 2 times negative 27, we end up with negative 54. Okay, now we replace the x with the negative 2. So we're going to have 2 times 3 to the negative 2. So the 2 stays out in front. We're going to take the reciprocal of -3, change that exponent of -2 to positive, and remember that we are going to first apply the exponent to the 3 and then the negative. So the negative stays out in front. We take 3 squared, which is 9, so we end up with 2 over -9, or -2/9. All right, f of 0. So anytime we have exponent of 0, it's going to result in 1 with the negative out in front. So we get 2 times -1, or -2. Let's look at the graphs of exponential functions. We're first going to consider if we put in a 1 for a c, and then we're going to swap out f of x for y, and we're going to look at y equals just a to the x, and we're going to assume that a is greater than 1. When we have an exponential function where the base is greater than 1, that is what we call exponential growth. We're going to plot a simple exponential growth example. We're going to use a equal to 2. All right, so that's greater than 1. We have some values of x that we're going to plug in. If we plug in a -2 to x, right, we get 2 to the -2. That's going to be 1 over 2 squared, and we get 1/4. If we plug in a -1, that just takes the reciprocal. We get 1/2. If we plug in 0, we get 1. If we plug in 1, we get 2. If we plug in 2, we get 4. All right, you might want to take a chance and just kind of work those out if you want. So let's plot these points and figure out what this graph is going to look like. So I'm going to zoom in here. We have that -2. We have 1/4. It's about right there. If we have -1, we have 1/2. If we have 0, 1. If we have 1, we get 2, and 2, we get 4. Okay, so if we connect these points, all right, we get the graph looking like this. Now let's look at some characteristics of this graph. So the domain we've already talked about is all real number. There's no restriction on what values that we can plug in for x. But what about the range? All right, there's no value of x that we can plug in that's going to make 2 to the x either 0 or negative. So the range is 0, but not including 0, to positive infinity. Now let's determine whether we have increasing or decreasing. Well, as we go left to right, the graph is only going up. So it is increasing only, and it's increasing on the interval for its whole domain, so the interval from -infinity to positive infinity. Let's look at x and y intercepts. So x-intercept, there's none, right? It doesn't ever cross the x-axis, so no x-intercepts. Y-intercepts, it has at 0, 1. The end behavior to the right, so in other words, as x goes to positive infinity, y values or function values are going also to positive infinity. And what about to the left? As x values go to -infinity, y values are approaching what? Well, this is just like in rational functions where we had asymptotes and y values approached one fixed value. We have that same thing going on here. Y values are approaching 0, but are never going to touch it or cross it. So that means we have an asymptote at the horizontal line, y equals 0. One observation to make about this graph and exponential growth is that it is growth because we have increasing from -infinity to positive infinity. Now we look at exponential decay. So we still have the setup of f of x equals c, a to the x. We're going to let c equals 1, and swapping out f of x for y, we get y equals a to the x. But now, for it to be exponential decay, we have to make the assumption that a is in between 0 and 1. So in other words, a is a fraction. So we are going to use the example y equals, put in a 1/2 for a. So it's y equals 1/2 to the x. All right, so now let's plot points to get the graph of this function. If we plug in a -2, If we plug in a -2, let's work that out over here. So we're going to get y equals 1/2 to the -2. So that negative means that we take the reciprocal. Well, the reciprocal of 1/2 is 2. We change the negative to a positive, and so we get 2 squared, and we get 4. Now let x equal to -1. So we get y equals 1/2 to the -1. The negative says we take a reciprocal, change the exponent to positive, so we get y equals 2. If we plug in a 0, 1/2 to the 0 is just 1. 1/2 to the 1 is 1/2. And 1/2, if we let x equal to 2, we get y equals 1/2 squared, so we have 1/2 squared, which is 4, so we get 1/4. Okay, now let's plot those points. We're going to have -2, we get 4, -1 we get 2, 0 we get 1, 1 we get 1/2, and 2 we get 1/4. Okay, so we'll connect these, all right, and we're going to get, this time we have a curve that is decreasing as we go to the left to the right. So let's look at characteristics. Again, the domain is going to be all real numbers, -infinity to +infinity. All right, again, the range goes from 0 to +infinity. It's all above the x-axis. And this time we have a decreasing function. And it is decreasing for all values of x. So as we go from left to right, the entire time it's going down. Y values are decreasing. We can see that in the values that we plotted as well. X-intercept is, again, there's no x-intercept because it doesn't cross the x-axis. The y-intercept, again, we've got 0, 1. And the end behavior to the right, as x values go to infinity, this time this is where we have y values going to this fixed value of 0. As x values go to the left, go to -infinity, y values are going to +infinity. They're increasing. The asymptote, again, is y equals 0. Okay, the reason we call this exponential decay is because of this decreasing on the entire domain. Okay, the last thing we want to cover from 4.2 is what we call the natural base e. This is an irrational number that shows up in a lot of applications, and this is where it comes from. If we take this function y equals, in parentheses, 1 + 1 over x to the exponent of x, all right, you can see it's graphed in blue there. It has an asymptote. It approaches, as x values go to infinity, it approaches a fixed value. So for this function, as x values go to +infinity, y values approach this fixed value, and it is this fixed value of e. Okay, so e is equal to this irrational number, 2.71828, and being irrational, it is non-repeating and non-terminating. All right, so we're going to continue with decimal places forever. That's why we use e to stand for that number. Because it shows up in a lot of applications, we do want to consider it as we study exponentials. So we're going to evaluate using a calculator. So f of x equals 3 times e to the x. So plugging in 3, we get 3 is that value out in front. E to, then now we plug in 3 for x. So this we definitely have to plug into our calculator, not going to be able to do this on our own. So I would suggest you practice this. We get 60.256, and that is rounded to 4 decimal places. So I'm actually going to put in the approximation sign. Now if we plug in f of -2, if we plug in 2 for x, we're going to get 3 times e to the -2. Plugging that into the calculator, rounding to 4 decimal places, we get 0.4060.